So we're talking about one population mean, sigma unknown. This one relies on what is known as the student t distribution. There's a whole little blurb about that. But let me get at this idea of degrees of freedom, because we do have to identify something known as degrees of freedom in order to carry out a t distribution, right? Because a lot of the characteristics of a t distribution are similar to that of a z distribution. And so the one difference is the degrees of freedom. So let's just tackle that real quick. So the little setup here is, assume that you have a sample set with 5 values whose mean is 45. How many values do you have control over? That is, you can select any number, any numbers you wish to be part of the set, but at some point you lose control over which numbers must be included. When does that occur? All right. So if you have a total of 5 values and their mean is 45. Right, so n is 5 values, the mean is 45. Right. Now the mean, by definition, is the sum of all the x values over n. Right, so we already know that this is 45. We don't know what this is, and we know that this is 5. So one thing that we can get out of this is that the sum of x, if I cross multiply, I just assume that this is over a 1. A couple arrows there. Good old-fashioned cross multiplication. 45 times 5 is 225. We'll double check a Ruski here. Yeah. And so what I'm saying is that I got 225, that value, to work with here. And we got to make some assumptions here. We're assuming that we're dealing with positive integers or whatever. You know, like you can assume whatever you want. That's what I'm going to assume. All right, so let me identify the first value, and I'm making this up. Let's say the first value is 15. All right, you make up whatever you want. If I subtract that from the total, I have 210 left to work with. So let's say my second value is 30. All right, so that leaves me with $1.80. All right, when I choose a third value, let's make it, just get things moving here. Let's make it 80. And let's say I choose a fourth value of 50. All right, what that means, because I only have 5 values to work with, that last value must be 50. All right, I indirectly had control over that, but I didn't directly have control over it. All right, so this one has been decided for me based on the decisions that I made earlier on. All right, so I decided that 15 was going to be part of the set. I decided that 30 was going to be part of the set. I decided that 80 was going to be part of the set. I decided that 50 was going to be part of the set, but I was not able to decide on that last value. It was determined for me. All right. So the number of values that I had control over was 4. All right. So 5 values in the set. I had control, I'll even say direct control, over 4 of them. All right, so I had freedom to choose 4 of the 5 values. So the n values in the set, subtract 1, the one that I had no control over, and what I get is the degrees of freedom of choice of values. All right, so degrees of freedom would be the number of values minus the one I have no control over this value. And so as it turns out, your t distribution is based on, among other things, mean, standard deviation. It's based off of the idea of degrees of freedom. So as the degrees of freedom increase, it gets closer and closer to a normal distribution, right? So, and that means indirectly or directly, however you want to think about things, that the n value, the sample size, must also increase in order to approach that normal distribution. All right. So that's kind of like a capsule summary of a pretty important concept in statistics. So I'm just giving you kind of the short version of it, but it's enough, hopefully, to get us into the process of conducting the corresponding hypothesis test. So let's flip to the next page, page 65. All right, so we're testing a claim about a mean where sigma is unknown. So simple random samples, sigma is unknown, so we use the sample standard deviation, and we have to assume normality, or have to be told that n is greater than 30. All right. Those are our assumptions. Anything that's verifiable becomes a condition. But you'll see that the null and alternative hypotheses, the alpha value part of it, the p is less than alpha component, it's all the same. All right. The only thing that's going to vary, actually really kind of from here on out, is the test that you use in the calculator, and obviously what numbers go into that particular function in the calculator. All right, so I think honestly, throughout all my years of experience doing this, I've taught it a bunch of different ways. The way that seemed to work the best is through example. So that's what I'm going to do. I'm just going to keep going into examples, and then in order to teach the concept, and then at the end we'll kind of pull it all together and tackle some mixed problems. All right. So we have a shrunken down version of this this flow chart that I created that's not on your handout. So just like the last video, that makes this a typo for somebody. Actually, there's two. One, the fact that this flow chart isn't in your handouts, and two, that alpha significance level. There should be a blank there instead of the alpha. All right. So example, the time it takes for students who drive to school on a daily basis to exit the school from their 8th period class. All right, so it was a high school related problem. The school had 8-period school day, so that would be the last period of their day. Start their car and exit school grounds approximates a normal distribution. All right, so looking at our conditions, we have approximate normal distribution, so that's accounted for. On February 3rd, 2003, the teacher had nothing better to do, time to sample 45 student drivers. All right. Now, it didn't say anything about being a random sample, so that's an assumption that'll have to be made. And determine the mean to be 5.7 minutes with a standard deviation of 2.1 minutes. Now, I couldn't possibly know the standard deviation of time it takes individuals to leave school in general. So this has to be a sample standard deviation. So sigma is unknown, so I'm using S. These three assumptions is what tells me that I'm dealing with a t-test. All right. We're using a 0.01 significance level test to claim that the mean time it takes for students in general to go through the above routine is actually greater than 5 minutes. All right. So mean. Well, we're looking for population mean. I already know that the sample took longer than 5 minutes. I want to see if that proves that the population takes longer than 5 minutes to leave school. The thinking behind this is 5 minutes is a long period of time, in terms of people trying to get out of a particular location, barring traffic and things like that. We're not talking about leaving Giant Stadium after a big win, specifically a big win, because after a big loss, most people are already gone by like the middle of the third quarter, so it doesn't really matter. Yeah, so I came up with 5 minutes. By the way, I'm the teacher. I had nothing better to do. So I came up with 5 minutes as my benchmark. And so I already know that the sample took longer than 5 minutes. I want to see if this means that students in general take longer than 5 minutes to leave school. All right. So what we have from this is that the mean mu is greater than 5 minutes. Or at least that's one of the claims. All right. So again, these two guys over here are my claims. Pen just turned off again. One of them is that mu is greater than 5. The other, same ingredients, just different sign. Mu is equal to 5. So these two are the only thing that differ between your null and alternative hypotheses. They tell us to test this at a 0.01 significance level. We know it's a t-test. All right, not just because it says it right here, and this is the example that goes along with that concept, but because we evaluated the three assumptions, and it fits with the information that's given. All right, so I'm going to stat test option 2. You have a choice between data and statistics, data and stats. All right, so the only time you would choose data is if you actually typed in data. All right, a raw list of data. All right, it's a common misconception. People tend to think typing numbers into the calculator. Numbers are data. No, a raw list of data would be the actual times of the 45 student drivers. All right, what we have here are summary statistics. So that's what we're going to put in. So we hit the right arrow to stats and hit enter. The mu sub o, same idea as the p sub o in the last hypothesis test, are assumed value. All right, so 5. 5.7 was, whoop, that's not a point. 5.7 is given as the sample mean, and 2.1 is given as the sample standard deviation, and there's 45 students. And again, we want a greater than symbol. I'm going to jot down the summary statistics here. X bar 5.7, S 2.1, and 45. Right. And again, that alternative hypothesis is what mu is going to be equal to. Mu is going to be equal to, or is going to be greater than mu sub o. So now I'm going to hit calculate. And again, the only thing I'm grabbing from this is the p-value. So 0.0152. All right. We compare the p-value to the alpha value. If the p-value is less than the alpha value, then we reject the null hypothesis. All right. Now, this alpha value was designated for us. They told us it's 0.01. 0.0152 is not less than 0.01. So we do not reject the null hypothesis. Now, you could see how flimsy this concept can be, because if I had selected a 0.05, I would have rejected the null hypothesis. So you could actually use a hypothesis test to mislead people. All right? The studies have shown, so what do the data say? What do the data tell us? Well, here, it depends. What do you want it to tell you? All right. In my opinion, and I mean, I would say it's a pretty learned opinion on the subject area, it tells us that the data is inconclusive, because for a 0.01, it fails to reject the null hypothesis, but for a 0.05, it would not fail. It would actually reject the null hypothesis. So, but because the person writing this had an agenda, we have to say that there's insufficient evidence to reject the null hypothesis. I'm going to use my circle draw tool because I can't physically make the oval. Reject the claim that the mean time, the population mean time, reasonable abbreviations are fine, to leave school is 5 minutes, All right. Always address the null hypothesis with the first sentence at the zero point zero 0.01 significance level. Therefore, the claim that it takes students longer than 5 minutes is going to be false. Oh, that's so brutal. Circle draw tool. There we are. And again, that comes back to the whole true-false thing, the check mark and the X mark. All right, so we are not rejecting the null hypothesis. So my null hypothesis is the keeper. The alternative is the loser. So that makes this true, and that makes this one false. All right. So again, I mean, there's no follow-up conclusion required, and you don't really know what the ultimate agenda was for the individual who was conducting the study. But obviously, it's not something that's conclusive, but you have the means now to convince people that it is. Right? So, at a minimum, if you could walk out of this class not being fooled by other people's BS, that's great. But if you can actually use this as a tool, that would be even better. All right, so that's where we're going to end it. And there it is.